Welcome everybody, Mr. Allen here. I'm going to try to do a quick summary here of sketching polynomials, kind of summarizing everything we've seen to date. I have a couple of videos on YouTube that I'll link to, hopefully if I remember, that have a little bit more detail as to why things happen. But today we're just going to focus on that they happen. So, starting point with anytime I'm looking to sketch is understanding the degree of the function. The degree tells me the basic shape. In this case, this is a fourth degree function. So right off the top, the other exponents, the fact that there's a 1 here doesn't matter. The fact that there's a 2 here doesn't matter. The fact that the 3's here doesn't really matter. It's not that it doesn't matter, but it doesn't affect my basic shape being a fourth power. And a fourth power looks something like this. So again, the degree of the function tells me how many directions my graph can go. In this case, my graph comes down, it starts going back up, down again, back up again. I can cover up to 4 directions. Now, depending on what these values are, that may look a little bit more flat. It may be that the maximum minimums are more extreme, but the basic shape having potentially up to 4 directions, I know based on this the fourth degree here. So that's a very big key to me getting going, is understanding that I'm dealing with a fourth degree function. If the equation is written in standard form as it is here in the black, no problem. If it's not, then it's maybe a little trickier to notice. Now, before I move forward, I just want to make the mention here. Somebody asked about this recently, so just remembering that f at x and y are exactly the same thing. Okay, so anytime I see f at x equals or I see y equals, I can use them completely interchangeably. There's no problem there. They mean the exact same thing. And maybe I could have, I'm going to pause here. And just to show that, here I have, you may not be able to see it very well, but the original equation on the other screen, the equation in black here. Here is, I should put it blue, the equation that was in blue on the other screen. F at x equals, you can sort of see that the only thing between these two that's any different is the one says y equals, the other says f at x. Otherwise, the actual equations are identical. And so as I turn this equation on and off, you can see clearly it is fitting the exact same curve, and so therefore it must be the exact same equation. So just wanted to point that out to make sure people know that if you see f at x or you see y, they are used completely interchangeably. Now, if I actually want to do this sketch myself, if I haven't got Desmos sitting there in the background, then I need to get my equation to factored form. So we've done a fair bit of factoring recently. Hopefully you trust that this equation and this equation are the same. And I suppose if you don't, I can do the same thing here, just kind of show when I click on this factored form of the equation, I'm getting the exact same curve, and obviously then I have the exact same equation. So getting there hopefully is fine. Now that means that if I have this though as a starting point, or if I've gotten to this point and kind of forgotten where I started, I need to be able to recognize that this equation is a fourth power as well, a fourth degree equation. How I can do that is basically just by looking at the various factors involving x and essentially understanding that if I multiplied this whole thing through, I don't really want to, but if I did, those x's would form one term out front. So it'd be a 4x times the x in each case. So 4x times this x times this x times this x, which would be a 4x to the fourth. Obviously matching this equation. So if I factored to get to this point, I must be able to multiply through, expand to get back to this equation. So understanding that multiplying these x terms will give me the first term of the standard form is all I really need. Now, if I did have some kind of exponents in these various spots, you want to recognize that this is still 4x. This is, if I expanded this one out, this would give me a term of x cubed. This would still be an x. This would expand out and give me a term involving an x squared. And so the highest power would have a single x here, times 3 more here, times 1 more here, times 3 more here, which means I would end up with a 1, 4, 5, 6, 7, seventh power at that point. So a 7th degree function at that point. Now, so that's sort of the basic understanding of the shape of the curve. If I know that I've got, once I know my degree, then I can know the basic shape. There are a couple of key features, of course. Knowing that an even numbered or even degreed function, so a parabola, which we've seen before and looks like this, or a 4th power, so a quartic, or a 6th power function, they all have the same basic shape of kind of a parabola with bumps, if you will. As soon as I see that even degree, I know that these are the shapes. And again, the way it works out is the number of the degree is the number of directions my graph can reach. The number, the maximum number. So for a 4th power, again, four directions. For a 2nd power or a parabola, it comes down, it goes back up, so 2 directions. A 6th power can do up to 6 directions. And then something that is an odd degreed function, if I have a cubic, it's only going to go 3 directions. So it's up 1, down 2, up 3. A quintic, a 5th power, will do up to 5 directions. 1, 2, 3, 4, 5. And if it doesn't do its 5 directions, just to be clear, what it's going to do is still just kind of a little bit less action in the middle here. It's still going to sort of cover, there might be just sort of understood to be up to a 5th direction in here, but we'll always have sort of the basic shape of starting in the negatives, ending up in the positives, starting in the 3rd quadrant, ending up in the 1st quadrant. Now, if you don't know that, so the question is kind of, how do I remember that? Well, to some extent, you remember it. There's only 2 basic shapes. We've got the parabola that comes down and goes back up, and then may have more, again, more minimums and maximums locally here, based on the fact that the degree is a 4, a 6, or an 8, a 22, whatever it happens to be. Or an odd numbered function that starts low and kind of comes back up. It's sort of just an extension of your straight lines from grade 9 that start wherever and go to wherever. Now, of course, they can go both directions, but you want to remember back in the day, way back in the day, this was a y equals mx plus b equation. If this slope was positive, so if the coefficient in front of the x was positive, the graph would increase coming from left to right. The same essentially is going to be true here for all of these. If the leading coefficient, if the first coefficient on the biggest term is positive, your graph's going to be increasing left to right. If it's negative, it's going to be decreasing from left to right, as was the case in, again, way back in grade 9, something like, negative 3x plus 7 would be a decreasing slope from the start. That doesn't change now. Even if I've got a 3rd power, a 5th power, the leading coefficient being negative would get my graph to decrease left to right. So if I just look at a few of these cubic functions, again, just sort of counting through the exponents here, I have an x times an x times an x, so it's a cubic. Here I have an x squared times an x, so it's a cubic. Here I have an x to a cube, so it's a cubic. They all increase left to right. If we put a negative in front, it flips in each case. So just again, the understanding being whatever I have here, if I'm multiplying that value by the x's, I'm going to have a leading coefficient, in this case of negative 2x cubed. The fact that it's negative means it's going to be decreasing exactly again as it was when we were in grade 9 dealing with straight lines at that point. I messed up something here. Yeah, we'll leave that and I'll fix it later. Last thing, maybe the actual, when I'm getting to the actual sketch. These factored forms, or these factors in the factored form, tell me where my zeros will be. And again, this is basically what we saw in grade 10, I guess, when we're dealing with parabolas. You would have only had 2 of the factors, but we know that from those 2 factors, we would end up with a 0 at x equals negative 2 and x equals positive 3. The reason that works out is we're looking for the x-intercepts, we're looking for the zeros. So essentially we're trying to solve this equation at that point. And we're saying, where are the zeros if my y value becomes 0? So if my graph is actually on the x-axis, the y value has to be 0. And the idea is that we're trying to figure out which x term in each of these cases gets me to that 0. Well, if x plus 2 is 0, then we know that x is negative 2. If x plus 5 is 0, solving this as a little equation, we subtract the x over, we end up with x equals negative 5. So we subtract x, we subtract x from both sides. That was very poor math speak to say that we subtract it to the other side. We subtract it from both sides. It is no longer, I have 5 minus 5 on this side, so I essentially have just the x plus a 0 on this side. And then I have a 0 minus 5 on the right-hand side, and I end up with x minus 5. Same sort of thing here. X minus 3 is 0, then x is going to be positive 3. And the last one might be a bit trickier, so we'll sort of write it out. Maybe I'll write it out completely. So 4x minus 9 is 0. And kind of if we go back to when we first started solving equations, what we looked to do then is basically add, in this case, 9 to both sides so that I can isolate the x eventually. I have a 4x, negative 9 plus 9 is 0. On the other side, I have 0 plus 9, which is just 9. And then the last step when I'm solving an equation, I have 4x here, 4 times x here. I want just x, which means this side is 4 times too big. So I'll divide it by 4, divide the other side by 4 as well. And so my last x here will be 4 divided by 4 is just 1, x on this side, and 9 quarters over here, which is, well, I shouldn't say approximately, it's exactly, which is exactly 4 goes into 9 twice properly, and 1 quarter, so 2.25. And so I have zeros at each of those locations. And again, if I flip back, hopefully that's what I'll see. Let's close off these ones that were not the ones I was interested in. This is the one I was interested in. And I have a positive 3. You can see if I can zoom that a little bit, I think. Oh, no wonder I had my zoom all the way down. But we can see that I have negative 5, negative 2, positive 3, and positive 2.5. Again, exactly the values, I hope. I wrote 0 here. It was a 3. So I'm looking for the value that makes this term, this factor equal to 0. So 3 goes in. And then I guess the last thing, sorry, I said last already, but I forgot. The one other kind of easy to determine point on our graph, we have the basic shape by knowing it's a fourth power. We have the the x-intercepts by solving each of these for 0. We would also like to know what the y-intercept is. The y-intercept is going to be, again, if I expand it out, the value that we end up with out here. So typically it will be, if there's a value out front, multiplied by each of the constant terms in our factors. And so in this case, there is just a 1 out front. I have -9 times 2 is 18, times 5 more is -90. -90 times the -3 is +270. So again, pick up a calculator if need be. -9 times 2 times -3 times +5. The y-intercept is 270. It's the constant value on the standard form, and it's the result of multiplying each of the constant terms from our factors in the factored form. So -9 times 2 times -3 times +5 gives me my y-intercept. And of course, if I go back here, that is at 270. So, one last time. Figure out the degree of the function. Obvious in this form, a little bit less obvious in this form, but basically just each x term that I have will multiply. If they have exponents on them, include the exponents. So this is 4x squared. That will be one of the values that I'd multiply to determine my degree. In this case, it's a square here, an x here, an x here, an x here. It's going to be a fifth power. That determines my basic shape. Basic shape is going to go 5 directions if I have a degree of 5, up to 4 directions if I have a degree 4, up to 6 directions if I have a degree 6, up to 3 directions if I have a cube, and so on and so on. And then determine where the zeros are, determine where the y-intercept is, I suppose plot them, and then draw on through. I've mentioned it before, but just in case we've forgotten, this value down here, the local minimum here, this value right here, the local minimum here, and the actual location of this, if it's not right on the, it looks like it isn't, so here it's going to be hard to sort of see unless I zoom in a lot. I don't want to zoom in right there though. I have a y-intercept of 270. There's another point kind of right here that is the local maximum. The local maximum. It's at 271.364. Now, you wouldn't necessarily know that, and it doesn't matter that you don't know that at this point. But again, just sort of understanding that we don't have in this class, in grade 11, grade 12 advanced functions, we won't have the ability to determine exactly where those maximum minimums are. We'll be doing that in calculus. So basically, if I drew this, and I sort of through this point and then sort of down into this general area here before I went back up, that would be fine. I don't know those values. I'm not going to find those values at this point. I will find my zeros. I will find my y-intercept. I will know the basic shape, and I will be done. So that ended up being much longer than I intended, and probably not nearly as valuable as I'd hoped, but we'll give it a shot, and hopefully somebody will gain something from it.